Hi everyone, I'm Neil Trevett and I work on developer ecosystems at Nvidia and I'm president of the Khronos Group. I'm going to give the latest updates on Khronos' work. We're bringing ray tracing capabilities actually to 2 of our open standard APIs, and I've been looking at the attendee list. It's great to see so many ray tracing luminaries here. Many of you guys know way more about ray tracing than I do at the coding level. But hopefully this ecosystem level update is going to be interesting to folks here. So let's dive in. So let's start quickly by introducing Khronos. If you haven't come across us before, we are an open standards organization. We are focused on creating interoperability standards to enable applications to access the power of silicon acceleration in domains such as 3D graphics, VR and AR, parallel computation. We are a non-profit. All of the standards we create are open and royalty-free. We've been doing this around 20 years now. We have about 160 members around the world, everyone from the largest companies down to small startups. And we are open to any company who wishes to join and have a voice and a vote in how any of our standards evolve. Here are the most active standards currently being developed by Khronos. There's 4 main groups. There's the 3D graphics APIs, including Vulkan and OpenGL and WebGL, initiatives around 3D asset formats, including GLTF, the OpenXR standard for portable AR and VR, and languages and APIs for parallel computation. But I'm going to concentrate on these 2 today, ANARI and Vulkan. I'm going to start with Vulkan. So why is Vulkan key to making ray tracing pervasive throughout the industry? Not only is Vulkan a new generation 3D API, it provides low-level explicit control over GPU hardware. It is unique and it is the only open standard new generation GPU API. And so it's not restricted to ship on only one vendor's platforms. In fact, as you can see here, Vulkan is now being shipped by pretty much every GPU vendor. It's being adopted by leading gaming engines and applications. It's available on almost every hardware platform, including desktops, mobiles, consoles, embedded systems, as well as cloud and streaming services. And so where Vulkan goes, ray tracing can eventually follow. So what is Vulkan's roadmap? The most recent version of Vulkan that shipped is 1.2, and that shipped in January 2020, so still relatively new. It integrated a number of proven extensions, including timeline semaphores and streamlining for apps migrating from DirectX and using HLSL. And the key ongoing roadmap discussions post 1.2 are on the right, and they include, of course, ray tracing, as well as variable rate shading, hardware accelerated, hardware encode decode. And this new functionality first ships as extensions. And those that are accepted by the developer community are strong candidates for integration into future core specifications. Now, the good news for this session is the first item on that roadmap, Vulkan Ray Tracing, has already shipped as an extension. It shipped in March. Actually, it's a set of extensions to the Vulkan API, but also the GLSL language specification and SPIR-V extension. SPIR-V is the intermediate representation that Vulkan ingests its shaders in. And all those extensions, they seamlessly integrate ray tracing into the existing Vulkan framework. And we regard this as a significant milestone. It is the first in the industry, first for an open cross-vendor, cross-platform standard API for ray tracing acceleration. And it's been designed so it can be deployed either using standard GPU compute, so it can run on any existing GPU, or if GPUs have dedicated ray tracing cores, it can take advantage of that too. So Vulkan ray tracing will be familiar to anyone who's used ray tracing in DirectX 12, which, as Adam mentioned, is called DXR. But Vulkan has introduced some additional functionality for load balancing ray tracing setup operations onto the host CPU, and we'll go into that in just a moment. One of the important points is the current ray tracing extensions for Vulkan, they're provisional. What that means is Khronos is welcoming developer feedback from the community before we finalize, and we'll look at the schedule for that closer to the end of the presentation. Okay, so how do you use ray tracing in Vulkan? So like many other ray tracing APIs. And again, as Adam was outlining, the first step is to build the scene geometry into an efficient two-level acceleration structure. So searching for ray intersections can be performance optimized. In Vulkan, the precise internal organization of those acceleration structures is opaque to the application, so that the hardware vendors can optimize it to match their own hardware architectures. And so Vulkan provides API calls to supply the geometry to be built into the acceleration structure by the Vulkan drivers. Once you have your acceleration structure, the second step is to launch rays into the scene to calculate how those rays intersect and interact with the scene geometry and the materials and the light sources, and to process those intersections with programmable flexibility. And that enables a wide variety of visual effects. And Vulkan provides two ways to dispatch rays into the scene. The first method is kind of similar to the first generation DXR. It uses a new ray tracing pipeline. It enables the application to compile a set of shaders into the pipeline to handle any desired ray and material processing. And then the application launches a grid of rays into the scene, with the ray tracing pipeline invoking the appropriate shader when intersections occur, or a miss shader, perhaps if no hits occur for that ray, which maybe you can use to render the sky if you're in an outdoor scene, for example. The second technique to fire rays, which Vulkan calls ray queries, is much more explicit. It basically enables any type of Vulkan shader to launch a ray at any time and process the intersection data however it wishes. So it's a very manual, hands-on process. It's a very flexible technique, because not only can the shader decide how to process that intersection, it can also control itself how the traversal proceeds through the scene. So what shading languages can a Vulkan application use to code all of these ray tracing shaders? Well, obviously GLSL is the default Vulkan shading language, and that can be used to generate SPIR-V ray tracing instructions. But over the last year, the Vulkan community has been working hard to also build a SPIR-V backend into Microsoft's DXC open source HLSL compiler. And that enables Vulkan developers with the choice of either using HLSL or GLSL shaders in their applications. And not only has that SPIR-V backend now reached production quality, and that is being used by an increasing number of AAA games to use HLSL shaders in their Vulkan titles, but Nvidia has extended that backend to support the Vulkan ray tracing extensions to generate SPIR-V ray tracing code from HLSL. So this makes it easy for developers who may wish to move their ray tracing shaders between DXR and Vulkan ray tracing, as substantially the same HLSL shaders can be used in both APIs, and you don't have to rewrite. So we have, our shaders. Regardless of the language you've used to write them, a ray tracing application can typically use hundreds or maybe even thousands of shaders to process the many types of visual effects and materials in a scene. Compiling that many shaders into a ray tracing pipeline can be intense enough to cause application stuttering when new scenes are loaded or when new scene effects are needed. And it can be particularly aggravating to discover that suddenly a scene needs one new shader, and that triggers the entire set of shaders for that scene to be recompiled and reloaded. To avoid that overhead, the Vulkan pipeline library extension enables a library of SPIR-V shaders to be incrementally compiled into an existing ray tracing pipeline, saving the need to recompile everything from scratch. So pipeline libraries, they can be helpful when dynamically managing the shaders in a scene, but there is always still significant setup processing for any ray tracing application, not just compiling the shaders, but also loading geometry into the acceleration structures. To help applications use all of the available processors in a system for setup processing, Vulkan provides the ability for the host CPU to build acceleration structures in host memory for subsequent download to the GPU, enabling the host CPU to perform setup processing in parallel with the GPU that may be performing other work. Also, Vulkan provides a more general purpose mechanism called deferred host operations, where the Vulkan driver returns a deferred work handle to the application for later execution. This enables the application to control work execution rather than the driver, and the application can decide to distribute the work onto multiple cores and background threads, for example. In a ray tracing application, deferred host operations could be used to asynchronously use multiple CPU cores to build acceleration structures on the host. So that's a very high-level overview of Vulkan ray tracing. How does Vulkan ray tracing and DirectX DXR compare in the details? The good news from the developer's point of view is that the two APIs share the same fundamental architecture, which makes it relatively straightforward to port code between the two, especially if you choose to use HLSL ray tracing shaders, as they can be used on both APIs with minimal changes. Both APIs have ray tracing pipelines, and with the recently announced DXR Tier 1.1 that was launched as part of DX12 Ultimate, DXR introduced inline ray tracing, which is the equivalent of Vulkan ray queries. DXR Tier 1.1 also introduced the incremental addition of shaders to a pipeline similar to Vulkan pipeline libraries. Though Vulkan is currently unique in supporting host building of acceleration structures, which together with deferred host operations can be useful. And Vulkan also has hooks for supporting cross-vendor debug tools such as RenderDoc. Before I get into the schedule for Vulkan ray tracing getting finalized, I want to talk about the growing industry trend to layer APIs over other APIs. It is relevant. This enables an application using an API such as Vulkan or DX12 to be deployed on systems where native drivers for that API are not available. This is becoming a quite widely used and proven technique. The new generation low-level APIs are an effective layering target, and the open source compiler ecosystem, including cross-compilers, is becoming increasingly robust. So for example, Khronos is layering to bring Vulkan to pretty much any platform, including Apple devices, by layering Vulkan over Metal, for example. But more pertinently here, another key layered implementation is VKD3D, which layers DirectX 12 over Vulkan. This is used by Valve and others to enable DX games on Linux, including streaming platforms. As ray tracing in games become pervasive, layered implementations such as VKD3D are going to wish to layer DXR ray tracing functionality over Vulkan ray tracing. And so the design of Vulkan ray tracing not only needs to support direct use by developers, but also act as an effective target for layered DXR implementations. And that brings us to the timeline for finalizing Vulkan ray tracing. Before the current provisional extensions were released in March, as Adam mentioned, Nvidia shipped a precursor vendor ray tracing extension called VK-Ray. Again, the good news for developers, those two sets of extensions have very similar architectures. And so if you've tried out the Nvidia VK-Ray extension, it's very straightforward to move any code you have to the new provisional cross-vendor KHR extension. As I mentioned before, the current Vulkan ray tracing extensions are provisional to allow developer review before finalization. And actually, I want to thank everyone, I think many people are here, who took the time to provide awesome feedback. For example, we've received a number of ideas for usability tweaks that's going to make the extension much cleaner to use. We also received significant feedback on streamlining support for DXR layered over Vulkan ray tracing, which is going to enable excellent performance and functionality for DXR ray tracing applications on Linux using Vulkan. In parallel to that specification being polished, that's ongoing right now. We've added support to the DXC HLSL compiler. We're finishing up implementations as a group. We're finishing the conformance tests. We've released some sample code, and the working group is pushing hard to get the specification updated just as soon as possible, definitely before the end of the year. And we expect that applications using the provisional spec will only need to make minor changes to use the updated spec. Almost finished. But before I do, I'd like to introduce Khronos' newest working group that was announced just at the beginning of March. ANARI is defining an API for analytic rendering or scientific visualization, which often uses ray tracing. ANARI, though, is at a very different level than Vulkan. It gives scientific visualization applications a portable cross-vendor API into high-level renderers, such as Intel's Osprey or Nvidia's Viz RTX. Those renderers, in turn, cool down into low-level acceleration APIs such as Vulkan or OpenCL or CUDA. Applications using ANARI will be able to simply provide data describing objects in a scene and let the renderer take care of all the rendering mechanics. And although providing portable access to ray tracing renderers was the key motivation in forming the ANARI working group, ANARI will be able to drive any type of renderer. So ANARI was initiated by Intel and Nvidia, and we've received strong support from the visualization community. We've just started, and these things typically take around 18 months or so to deliver a final specification. If anyone here is interested in ray tracing for scientific visualization as well as games, please consider getting involved to make sure this new API meets your needs. So that's it from me. I hope that was a useful update. And again, if any of these Khronos standards are relevant to your business, any company is welcome to join Khronos to have a voice and a vote in evolution. So thank you for your time, and happy to answer any questions.
Great. That was great, Neil. Thank you so much. I'm going to see if we've got any questions here. So there's one. Do you think ray tracing will keep just the way of rendering lighting, or it can evolve to something else that interacts, that can be used not only in games but in simulations?
Yeah, no, that's a great question. I think ray tracing is in the end just a mathematical construct. You can use it for anything where you need to understand how you're interacting with objects or scenes that are defined by geometry. I mean, a great example was chatting to John Petty earlier, and a great example is you can use it for audio. You can use ray tracing to figure out how audio bounces around a scene, and certainly in many simulation type calculations, the basic calculations that you're undertaking for ray tracing can be very applicable. So as people, I think, begin to understand ray tracing and understand how it works, I think you will see all kinds of applications that use the technology, not just games or rendering applications.
Okay, great. Let's see, I think there's another one here too, yes. As a starting graphics programmer with minor experience in ray tracing from making a real-time CPU ray tracer and some OpenGL experience, both ES and normal, would you recommend starting with a Vulkan or a DXR ray tracing project?
Good question. I think either is fine. DXR is final right now. The Vulkan provisional specs are still provisional, so DXR is a little bit more advanced, but really Vulkan is not going to change that much, and you can take any code from Vulkan to DXR and vice versa. So with whatever you choose, I don't think you're painting yourself into a corner. I would just say, just go with what you're most familiar with and most comfortable with, and either DXR or Vulkan would be fine right now.
Right. Okay. There was one more. I think this will be maybe the last one. When do you think Vulkan Ray Tracing API will be finalized?
Great question. We have a rule at Khronos, try not to paint ourselves into corners. But if I was a betting person, and this is just my personal view, it is going to be, we'll get the next version of the spec significantly before the end of the year. And I think that hopefully will be close to final.
Okay, right. Oh, okay. So we've got a couple more, and then we'll stop for the next speaker. But there are two here that are specifically for you, Neil. So let's just get those to you.
Mm-hmm.
Are there any benefits to using Vulkan to render offline?
Sure. Yep. You can use either the APIs. You don't have to be rendering to a screen in real time. You can be rendering offline, and both DXR and Vulkan, they both provide the programmable capability. So you can do production class rendering with Vulkan if you wish offline, as well as using it in real time applications.
Okay, great. And then there's one other question here. When will the non-beta NVIDIA drivers be released?
So that is the same question as when will the API be finalized. So no hardware vendor can ship a production driver, a non-beta driver, until the spec is finalized. As Adam was saying earlier, we at NVIDIA, we typically try to have the production driver on the same day that the final spec is made public, and all things being equal, that's what we'll aim for this time around too.